Good morning. Can you hear me in the back? So I know most of you are really software engineers, and you're interested in how software is part of a larger system. Because one reason software is critical is because it provides critical functionality to the proper behavior of the bigger system. So I'm going to talk about an approach, a holistic approach, for understanding what that whole system is about, and what part does the software play, and how can you make the system behave by making the software behave properly. So I'm going to focus on systems principles and concepts. So 4 topics today. The first is the concept of holism, because it's difficult to understand what a system is about without understanding what holism means. So then that leads us to the concept of a system. And I came to Japan the first time 12 years ago to teach at Keio University, because they were asking the same question, what is a system? Because they were trying to teach their students on what is a system. Because if you're going to design, create, and build systems, you need to know what the systems are. So, actually from teaching, I needed a way to explain to students the attributes of a system. So I developed a theory I call the PICARD Theory. And I first developed this when I was teaching over at Mitsubishi Electronics, Melco, because before that I was having a difficult time teaching about systems, because systems is up here in the mind, it's an abstraction. And many people have a hard time dealing with the abstraction of systems. It's not like hardware, which you can touch, or software that you can see the code, you can see the instructions in the code. So many parts of the system are not tangible, you cannot see them. The whole notion of the system is not tangible. But what you want is systematic and systemic behavior that has a positive outcome to society. That is why we create systems, to change society to be better. So after looking at the PICARD theory, I'm going to show you an application of these principles and concepts in the theory, in what I call the 7 samurai of system engineering. So what is holism? Well, we can look to philosophy to help us understand holism. And it's all about parts of a whole that are interconnected. That's what makes the system work. Is the part interact in such a way to give you system-level behavior that you desire to have. And the key part of that is the whole is greater than the sum of its parts. In medicine, and this is even more true in Eastern medicine, where they take the Taoist or Buddhist approach, they treat the whole person. In fact, they consider part of the person is more than that individual, but it's the family, it's the neighborhood, it's the society. We treat the whole person by treating the bigger system. It's a holistic approach. Take into account mental, how we think, and social factors. A lot of our illness is not from ourselves, but how we interact with others. And so a lot of our physical illness is caused by social illness. So we can treat a person in the context of their society and their family, so that is a more holistic approach. And the medical community is learning that they can treat people in a better way by taking a holistic approach. So all of engineering is based upon the philosophy of René Descartes, the Cartesian approach. It's called system analysis, where you decompose a problem into smaller pieces. That's the Cartesian approach. But when you do the Cartesian approach, we call that things like functional decomposition. We think of the big function, we decompose it into subfunctions, and smaller sub-functions, and eventually have you get the lowest level functions, and you either build that into your hardware design or build that into your software algorithm functionality. So that's a very important part of engineering, but system engineering is that plus the holistic approach. So it's reductionism plus holism. So it's analysis plus synthesis. So synthesis is the missing part that a lot of people who start with engineers try to become system engineers. They don't realize they need to add on top of analysis, synthesis. So synthesis is taking everything back together and put it back into the whole thing. The holistic synthesis of the parts. So the analysis decomposes the parts, and then put the parts back together into the system. So, what is the system? The system has holistic properties because the parts of the system need to come back together into a whole. So you need to understand when you engineer the system, how will those parts come together to make the whole system. So every system has a boundary, and we are going to be dealing with parts of that system, where software is a part of the system. And the system often has value to the extent it interacts with things in the surroundings. So we often talk about the interaction or the interfaces between the system and external elements. So now we get to the theory. This is a systems theory. This is a theory of how do systems work. So what do I mean by PICARD theory? So the system is a holistic, it's a summation of these elements. So yes, the parts interact. That's what the definition of the system says. It's an interacting part, but it's in a given context. So we don't understand the context. The interaction between parts may not give you the proper behavior in one or various contexts. So by looking at these parts, we have to look at what does each part do, the action performed by the parts. And the action of the parts in the context gives you the interaction between each other and with the surroundings. And a lot of behavior is a function of the relationships between those parts and between the system and external elements. And the last element is the destination. In other words, what is the desired outcome of this new system? So you need to know what the destination is when you start. So this theory is a theory of how systems work, and it can be a way to help you see the whole system. So when I see people working on the system, they're often not working on the whole system. They're working on the thing they're responsible for. My piece of code, my software item, my hardware device. But those things are always part of a system. And when you're working on that part, so most of our engineers are working on an individual part. They need to understand how that part works in the system and how the system works in a context. So that's what system engineering is responsible for doing, is taking all the part engineers, working with the part engineers, to understand how those parts contribute to the whole. So there's a common belief, I think a misbelief, that system is a thing. And we often talk about the system as a thing. We will point to something and say, that is my system. That is my system. But I think that is a misperception. So we need to, through holistic thinking, be able to see that it's more than that, just that thing. It's more than just a part. So what is meant is a more holistic viewpoint and a broader perspective. And I believe this PICARD theory is a tool that will help you have a broader perspective. So let's go back to 1975, Gerald Weinberg. Gerald Weinberg is a software engineer. He understood systems. And a very, very, very good book. I highly recommend this book, General Systems Thinking. What he said in there is a system is a way of looking at the world. Notice he is not saying the system is that thing. He's saying the system is the way I look at that thing, which is different than saying that is the system. You say, I see that thing as the system. That is different. That is very different than what we teach our system engineers, and I think that's a mistake. Because when you treat the system as that thing, then you're really looking at just the parts, and maybe some interactions that you can see. And we put that down in terms of interfaces. We define the interface and the order requirements about the parts and about the interfaces. That is a limited view of what the system is about. So he also said, a system, any system, is the point of view of one or several observers. So we'll come back to this point after we look at the theory. So we have a thing. People often call that thing the system. But the thing, there will always be observers. Some of the observers are engineers, but some of the observers are the users, the maintainers, the operators, the owners. There are many observers of that thing. Not all observers will see that thing in terms of a system. But it's our job as system engineers, through holistic thinking, to be able to see the systemic properties of that thing. So Gerald Weinberg said the system is the way you look at this thing from this point of view. And what you see is an image. The image, the total image of the system is a collection of views of different aspects. For example, you can have the safety view, you can have the security view, you can have the usability view, the manufacturability view, the operations view. There are many different views that are important in building up the entire holistic image of the system. So if you have a second observer from a different point of view, what that observer sees is a different system. So that was another mistake with people talking about the one system. Well, saying if the system is the way you look at the thing, then different observers will see different systems. So that gets back to our synthesis. If different observers or different stakeholders see different systems, it's our job as system engineers to understand all those perspectives and be able to integrate those ideas back into a holistic image of the entire system, not just the system from individual perspectives. So we can draw a conclusion from what Gerald Weinberg says. If the system is a way of looking at a thing, then if you have multiple observers, you have multiple systems. Very key point. Our system engineering teaching, our textbooks, our discussion does not recognize this essential fact about systems. So I'll give you a real example. When I was in school, I learned about the solar system. The solar system was the sun plus 9 planets. But later, the sun plus 8 planets for the solar system. So the system changed. And why is that? Because the astronomers, from their point of view, were trying to understand how the solar system works. And they found that by looking at it as 8 planets instead of 9 planets, they were able to get a better understanding of the system behavior. Now, planet number 9 did not go away. They just reclassified it as something else besides the planet. So that's a lot of what we do when we're doing system analysis, is identifying what are the parts of the system. Here's one part, the sun, and 8 parts over here. And those 8 planets interact with each other and interact with the sun to give you the solar system behavior. Okay, so the 9th planet is now called planetoid, has a different behavior as a contribution to the solar system. But the story continues. Just last month, the astronomers are wanting to put Pluto back into the solar system. It never went away, but they're reclassifying, okay, we looked at it without Pluto as a planet, but now if we take Pluto back in, do we have a better picture, perspective of the total system? So it is our choice about where the boundary is for a system. We need to choose what are the parts inside the boundary, because that affects what are the interactions, what are the relationships, and it affects our understanding of how that system can contribute value to the end users. So we must choose carefully. Most of our system engineering teaching the first step is to draw the boundary of the system. And then they say, look at the data flow in and out of that system. But that presumes it's obvious where the boundary is. But if you draw the boundary in the wrong place, you might have bad behavior of the system, or it make it difficult to understand the real system. So we need to choose carefully where the boundary is, because that affects our understanding of the system. So here are several questions of parts. So where is the system here? We can look at interactions between the parts, and maybe these things have high interaction between them, and then maybe we can say, this is the system, that's another system, that's another system. But if we take a different perspective, if we look at relationships instead of interactions, we get a different perspective on what the system might be. We can also look at maybe the different properties of those parts. And maybe all the red things is one system, the red system, and all the green things is the green system. So we need to explore different ways to partition our system to classify the parts to help us understand better the interaction and the relationship. So let's look at an example. Let's say we have a problem with this part. The part is causing misbehavior. It's not giving us good results. So if we draw that as a system, we might try to focus on making all these things work better together. But if we take a different perspective, we might discover that instead of solving the problem right there, maybe the source of the problem is over here. Maybe it's not a function of interaction so much as a function of relationship. So we need to examine the system from different perspectives. Sometimes focus on data, sometimes focus on relationships, sometimes focus on performance. Understand the different aspects, different ways of looking at the same as a system. But the common perception that the system is a sum of the parts. So here is the system. Many people in the faith community will think this is the system. Well, these are the parts. Now they do come together into a whole part, a bigger part. But even then, that is not the whole system. That is really just a part of the whole system. So we have different names for the parts, and it depends on your domain. Some domains, they call them subsystems, some call them elements. In the software world, they tend to talk about element components, software items, and software units. In the hardware world, they tend to talk about devices, products, and elements and subassemblies. So don't get confused by the labels, they're still all parts. They're just different names for the parts. So part of what we need to do when we analyze the system is identify all the different parts and even identify what we call the parts. Because we're going to be dealing with different disciplines. Mechanical engineering, electrical engineering, software engineering, and they will have different names for these parts. So we will understand the whole system, but they will understand part of the system. So what are the parts of this system? You know, it's very common with the camera. Everybody has experience with a camera. So it might be maybe obvious that there are certain parts of the camera. The lens, the flash, the electronic circuit inside, the user interface. But is that the total system? Well, there are other things that make this system behave properly. Without the proper carrying case with the proper properties, you may drop the camera and it may damage it because the carrying case does not interact well with the camera and with the floor. The shipping container, shipping it from the factory to the store. If you don't have the proper shipping container, it may not function properly when it arrives. The instructions. you can have complex operations, if you don't have a way to teach the operator how to use it, that is part of the system. There's an interaction between the user and the instructions and the user interface unit. And we often don't even, how many people in their system diagram put the instructions as one of the elements of our system? When we make system diagrams, we tend to take the tangible items and only show those in our system diagrams. So we need to take a more holistic approach in our modeling methods and tools. We need to take account of things, well, how do you model the techniques for holding it? Because the quality of pictures may be a function of how you hold it. So in the instructions, you may need to explain the technique, and then maybe even explain the technique in the user interface unit, and maybe encode some of the technique in the electronic circuit. So notice how there's relationships and interactions between these parts and those parts to make the whole system work. Extra batteries, because batteries have a certain life, and if you expect that they need to use it for longer than the batteries will last, well, extra batteries might be essential when they have a good behavior of the system. The printer, getting the pictures out of the camera and onto a piece of paper. How does the printer interact with the camera device? The patent. The patent is key technology that you assign ownership. You assign ownership by being granted a patent, and that gives your company competitive advantage over other companies. The patent may be a very important part of this total system that makes the business successful. So you need to think of your camera business as part of the system. That's part of the context, and what makes that business successful could be patents. So take a wider view of what are the parts of the system, and you get a better understanding of what makes a successful system. And even beyond just the device itself, what about the user? There are people involved in all of our systems. So the interaction between the user and the device could be very important. The human system interface. It's also important to consider the environment within which it will be used. Will it be used out in the open, underwater, out in space? If we don't consider the environmental parameters that affect the operation of the system, we may not get a successful system. So even the things in the environment may be part of these more holistic, bigger systems. So what types of parts constitute a system? It's very traditional for system engineers to say it's the hardware and software. And more mature system engineers will say, well, there's people also part of the system. But there's really more than hardware, software, and people. There could be the facilities. The facilities may play a crucial role in the success of that system. There could be the data, like the instruction manual. Could be materials. Could be special materials that make the thing last longer and better performance. There may be services. Nowadays, with our interconnected world, everything's part of the internet. Everything's an internet device. Well, we're connecting to what the internet does is connect us to all these services available in the World Wide Web. So that's become a crucial part of most of our systems now. And patents. Techniques for doing things, for building things, manufacturing things, for using things. Those are all patentable ideas that also contribute to the success or failure of systems. So it's more than just the parts, how they interact. So here are 8 parts. How many ways to interact? Well, if we just look at simple one-way connections, there's 28 connections, 28 ways to interact. If we do two-way connections, there's 56. But if it's more than two-way, many of our interactions are 3-way, 5-way, 6-way. You get 8 factorial, 40,000. Just 8 parts, 40,000 ways to interact. But if there's different kinds of interactions, then that number approaches infinity. So the more parts we have, the more interactions, the more difficult it is to understand how the system behaves, and does it behave properly. So we need to understand it's more than just binary interactions. There may be multi-binary, n-ary interactions. And a lot of our modeling tools and techniques are limited to binary connection building. So our thinking is limited by the tools we use. A lot of our modeling tools have not advanced to taking a more holistic perspective that allow us to analyze the complex interaction of our systems. So in exploring the behavior of those parts and how they interact, we can explore different ways to interact. And each of these patterns will have different properties. You might have different performance, different levels of safety, different levels of security, different usability, different manufacturability. These are all the things we need to consider when we're looking at different ways to interact. So going beyond interaction, there's another key element, which is the context. So we saw a system is a boundary, and outside the boundary in the surroundings are elements that we interact with. So the context is really all things in the surroundings that are relevant to a proper system behavior. So let's look at 4 parts in one context. These will interact with things outside the boundary. But there might be a different context. The same parts interact with other things. So it's common that we only look at a single context for our system and don't look at the multiple contexts, the multiple environments our system might be operating in. And in each environment, there might be different things we need to consider. So here is an extra level of complexity of analyzing our systems. So going beyond context, we have actions. What do the parts do? But just the parts doing their actions doesn't give you behavior until you combine the actions with the relationships to give you interactions, because it's the interactions that give you the holistic properties that we find beneficial in our systems. So engineers have it's very common to do functional modeling, data flow modeling, object modeling, to identify the actions of the system. And then we typically allocate the actions to the parts of the system, and we call that functional allocation. So if we consider different contexts, in one context, action 1 is followed by action 2. But if there's another context, action 1 might be followed by a different action. So if we limit ourselves to only looking at a single context, we might miss some important behavior in a different context. So it's important for us to understand the wide variety of contexts within which our systems will operate. So going beyond action, there's also relationships. There are different kinds of relationships. Most of our engineering modeling tools will focus on functionality. We call that functional analysis. But there's some types of systems, for example, flight control systems, where they're event-driven, and it's very important to look at cause and effect, because you're trying to affect the behavior of the airplane or the spacecraft by flight control. So the event-driven cause-effect relationships can be very, very important for certain types of systems. Some systems, their behavior is driven mostly by the topology. Communication systems is an example of that. It's more important to know how the network elements are connected by links communication than what the nodes in the network do. So the topology of a communication network is a large part of what drives the useful behavior of that network. The ordering for some type of system, the sequence of the events by which, like for example, a launch vehicle putting a spacecraft in orbit, the order in which the action happens during launch is very, very critical. If you get something out of order, then something bad might happen. So a lot of the testing we do for our systems is really checking the proper order of things. Do they happen in the specified order to give us good behavior? When we go to systems that include people, then we have to take account of interpersonal relationships. Family, friends, how we organize, how we do command and control, who has the authority to make decisions. These are all about social relationships. So part of our system that includes people need to take account of the interpersonal relationships. Now, engineers often are more of a mathematical orientation. So engineers tend to focus on this sort of stuff. Engineers have difficulty dealing with social systems. But when humans are part of our systems, how will engineers be able to model and understand the interpersonal relationships? So what this tells you is part of your system engineering team, maybe you need to be some non-engineers. Maybe you need psychiatrists, sociologists. Maybe you need anthropologists. You need a different sort of person who understands the people aspects of our system, the interpersonal relationships. So a very simple example of relationships. Entity A related to B. So here's an example of a cause-effect relationship. Rain causes wet ground. Very, very simple. But this is only one relationship that may be part of hundreds of relationships that make the total system work. You can have spatial relationships. Balls inside the box. And putting the balls inside the box gives you certain behavior. If you put the balls outside the box, you may get the wrong behavior. So you need to understand the proper relationships so you can design your system to always have the correct relationships. Roads bring traffic to and from the building. Now we're getting a little bit more complex relationship. Well, how does it come to and from the building? Is it a circle? Is it a line? Is it a path through? There's many different ways that you can string a road to and from the building. So here's an example of some relationships of an observing system architecture. And I did this 2 times. One with our government agency that's responsible for National Weather Service, a National Oceanic and Atmospheric Administration. And the second time I did this was within our own NASA, because NASA and NOAA both are dealing with observing systems, observing the environment, observing the Earth. So they have observing systems that will take measurements of environmental parameters and will provide that data to some sort of system that will turn that data into information that's provided to users. So here are 3 different kinds of entities and 2 relationships. A user is a type of stakeholder, and stakeholders have requirements on how they expect the system to provide value. So engineers will turn stakeholder requirements into service requirements. So we were dealing with the National Weather Service. So they have service requirements like, tell me if it's going to rain tomorrow. Tell me if that earthquake will cause a tsunami to come to this country, and when will it come, and how damaging will it be? It's raining up in the mountains. Will that cause a flood to come down these rivers? Because the reason we do weather forecasts is to predict the future so people can take the proper action. To maybe avoid damage, avoid loss of life. So that's why we have observing systems to predict the future. The farmers would like to know, will it rain next month, because they need to plan the planting of the crops and the harvesting of the crops. So they use weather prediction in an economic manner to maximize the production yield of their crops. So we have many different stakeholders who have different needs of these observing systems. So the phenomena are things like tsunami, typhoon, earthquake, flood, rain, wind. Those are the types of phenomena that people care about in the environment. So in the observing system, it contains sensing elements that will take measurements of certain parameters of the environmental phenomena. So let's say phenomena of a typhoon. What parameters of a typhoon do we care about? Well, we care about the wind speed, wind direction, precipitation, precipitation density, wave height, ocean temperature. So the weather forecaster who's trying to understand the typhoon needs to have all the data from the observations, and they collect the data and send it to data analysts so they provide a hurricane forecast, a typhoon forecast to the users so they can take appropriate action. So these sensing elements are usually situated on platforms or stations. The platform could be a satellite, it could be an airplane, it could be a ship, it could be a stationary platform mounted on the ground. So this is another aspect because it determines the location and if that location is fixed or moving. Because all these features have an effect on the total set of observing systems and how they behave as a holistic enterprise called National Weather Service. The observing systems have some organizational relationships. They're operated by one or more operators, they're supported by one or more supporters, and they're owned by some organizations. So these may be different organizations involved in this observing system. The system is often part of a larger system, and it's often controlled by a separate system providing control. So this is a single observing system with all of its relationships. So this helps NASA and the National Weather Service understand there are 50 or 100 different types of systems and how all of them contribute to providing basic services. In NASA's case, that was answering research questions of the scientists. In the case of the National Weather Service, it's providing weather services, climate services, geographic, oceanic services. So they're providing data so people can make economic decisions. And finally, the seventh part is the destination. So we have a current situation and we're trying to achieve a different situation in the future with a positive outcome. So we need to understand what impact are we trying to have as we try to make sure that there will be some negative impact and some positive, but the net impact is positive because why build a system that will have net negative impact? So we need to understand the sum total of the impact, and this will be driven by the purpose. So we need to understand the impact so we can establish the purpose. And the purpose of the system that helps us understand the requirements we place on the parts of the system. So it's a very important principle to begin with the end in mind. What outcomes are we trying to achieve? So going back to what Gerald Weinberg says, a system is a way of looking at the world. That thing is not the system, but the way we look at that thing is the system. The system is a holistic image of parts, interaction, context, action, relationship, and destination, hence the PICARD theory. So having understood that there's multiple points of view, multiple observers, the image of that thing is really a reflection of the views of the various stakeholders. So we need to identify the various stakeholders, those who are impacted by the system, so we can better provide them a solution that gives everybody positive impact. So the PICARD theory can act as a special tool, a lens, for having a better understanding, the way of looking, the better understanding of the systemic properties of that thing. So we look at these elements and relationships. What are the systems? The system operator, really, these are the things the operators observe that see. So this is you might say, the operating system. But the user will be concerned about these things. So those, even in the set of things, there are more than one system because we have different observers. The developer's perspective is only the things they have some impact on designing. And they have to understand the boundaries because they define interfaces. These are the things they control, and these are the things outside their boundaries, outside their context. The observation community Their main concern was the largest system that has operating systems and two operators, and what the parameters were measuring. The observation committee doesn't really care about assisting on this. They only care about what things are being measured by the observing system. So notice a single element with relationships. There are various systems, different systems, and it's all those systems combined that give us the entire holistic image. So it's a special job of the architect to understand those various perspectives and the various systems, and through synthesis, make sure they all come together and give you a holistic image of all the pieces. So the PICARD theory is a way to help you have a better way of looking at the world. Don't look at the world as just a mechanical engineer, software engineer, electrical engineer, but as a system engineer, you need better systems tools like the PICARD theory that can enhance your ability to look at the world in the proper way. So now I want to take this PICARD theory, show you how these principles and concepts can be applied using the 7 samurai. So most of you older people will have seen this many times. I taught a class at Cato University yesterday with 30 students in the room, mostly young. Only 5 out of 30 had ever seen the movie. Well, I'm sure most of you have, because it's now about 60 years ago, 1954, the Kurosawa. I first encountered this movie in college when I took a class on film. And we looked at various directors and various ways to put movies together. And to me, this movie made a big impression upon me. Now, I didn't realize until 10, 15 years later what impression it made until I was working on systems. When the ideas of looking how the 7 samurai had to work together to solve the problem. Each samurai by themselves was very strong and cunning, but an individual samurai could not solve the problem. Because what was the problem? There was a Japanese village, and these thieves were coming around harassing the villagers and trying to steal their crops, steal their women, and trying to cause lots of trouble. So the villagers went to the samurai and said, "We need your help." But the samurai realized the leader of the samurai, he could not do it by himself, so he had to recruit helpers. So that's what we do as system engineers. We may have the main thing we're designing and building, but we may need to have our main system work with the other systems in a more holistic system of systems. So we can learn some things by understanding the story of the 7 samurai. So the first of the 7 systems I call the context system. System number 1. And the reason we look at the context is because there is a problem that somebody has pointed out to us. So this problem might be stated in terms of a requirement document, or a mission need document, or maybe a science question, or maybe a business objective. So we state these problems in various ways. So we look at the problem, but we need to be careful. Don't just solve the problem. You may need to solve something in the context, because there may be a cause effect. There may be something causing that problem. So if we just address the problem by itself, we might not address the whole problem. You can think of the context system as really the whole problem, not just the visible problem. It's like an iceberg. The tip of the iceberg is above water, and that's what we see. But the whole problem may be underwater. The whole problem may be bigger than just what we see. So the problem is in the context, and it has interactions with things in the context, and some of those things may be causing that problem. So that's why we need to look at the context as the system itself. And there may be multiple contexts for that problem. So if we only solve the problem in one context, we may have the problem reoccur in some other context. So that's why we need to put various contexts, various things in the context, and understand how everything interacts and all the relationships and interactions. So here's the kinds of things that you have, system elements, you might call them, in a context system. There may be somebody's pre-existing solution. That was the system we put in place 10 years ago. In fact, that old system might be causing new problems. There's the physical environment itself. There's the regulatory. Laws and regulations may have an effect on the problem. There is the information that's available in the context. There's the knowledge. But there's also some other things we often don't consider is anti-knowledge. Things we think we know that are not true. There are people who will purposely give misinformation because they are trying to deceive you, or maybe they don't understand, or maybe there's some politics where people are trying to convince you to do something you don't want to do. So, but that's part of the context. It's not just a technical context, it's social context, political context. There's also the way people feel. That's part of the context. There will actually be people in the context who love the problem. They don't want the problem to go away. So what we focus on is the people who hate the problem. But if we don't understand the people that love the problem, take cars, for example. Cars don't last forever. The users of cars want them to last forever because it's very painful when your car breaks when you're going somewhere. Okay, but who loves that problem? The car mechanics love that problem because they benefit from the problem. So if you make cars that never break, then the mechanics will be against you. So to have a total solution, we have to understand all the feelings out there, not just those who have a problem and hate it, but also those who like the problem, because you need to take them into account, because sometimes they can come back and make your system less than successful. The entire context, not just those who declare the problem. There's also some aesthetics. The aesthetics will also affect how people feel about the system. So it's not just a technically correct solution. It's not just technology. It's also, do people feel good about what they see? Is it elegant? Is it simple? It's a lot of the aesthetics that lead to usability. So we talk about user-friendliness. Well, aesthetics can have a big impact on the user-friendliness of our systems. And when systems are not user-friendly, that means they're difficult to use. That means they may be less secure. Means they may be less safe. So aesthetics may have a big impact on the success of your system. So notice if you look at all these system elements all together, you may need to spend quite a bit of work understanding the entire context system before you even try to solve that particular problem. So we system engineers, we're going to engineer a system that will intervene to try to address that problem, to eliminate the problem, to suppress the problem. Now we would like to make the problem go away, but often we don't make the real problem go away. There is something in context that's causing the problem, so we make the problem go away. It's like a symptom. Like a doctor could treat the pain, but unless they treat the cause of that pain, so some other illness may show up in some other place in the body. So they need to take the holistic view of the person, the whole body, and the family and society around that person. So intervention, what does that mean? Intervention is the action you're going to take to improve some situation. Now notice it doesn't say action taken to get rid of the problem. You're trying to improve the situation. So you have the current context and you want to change the context so the problem is less hurtful to certain people. So intervening means you're trying to do something to influence what happens. You're trying to interfere with the outcome or course of events. If you did nothing, what would the normal outcome be? because he wanted to achieve some different outcome. So let's just take two problems, for example. One is transport people quickly over long distances. One possible solution is a passenger jet. Okay, now there may be other solutions. There may be a boat, there may be a car, there may be a train. Okay, so we need to examine what are the different parameters. How many people, how fast, what distance, so that's part of the context. All those questions are dealing with the context. So this may not be the right intervention depending on the context. So that's why to get the right solution depends a lot on our understanding of the context system. Second problem is collecting images quickly over the entire Earth. Now, as a spacecraft engineer, it's natural for me to think the solution is always some sort of satellite. So that's one problem is we come to the table with preconceived solutions. So our understanding of the context is colored by our background, our culture. As an engineer, I think the solution is always a technology solution. If I'm a businessman, I think it's always a business solution. If I'm a politician, I think it's always a political solution. But there may need to be a holistic solution to the holistic problem. So to bring this intervention system into being, we need another system called the realization system. Think of this as your development project or your engineering business. It's really context for the people that are going to be working on the intervention system to bring it into being. So what's the intervention system for this passenger jet solution? Well, it's more than just the company developing. It may also be the organization that operates the system. Because it's not good enough just to build the jet, you also have to use it in a certain way. There may also need to be a set of standards for the airplanes that make them safe to operate, and so on. So the realization system is more than just the development organization. So look at the imagery satellite. Well, you have the satellite developer and builder, but for large complex systems, they often depend upon many suppliers of the parts and subsystems. So Boeing by themselves cannot build satellites. They need a complex network of suppliers that gives them the entire realization system to most effectively build imagery satellites. They may also need the U.S. government to enable this system by providing funding. They provide the problem. They provide the context in which they're going to operate it. The regulations on what you can and cannot do with satellite. The technology, maybe a key component. The knowledge of physics, and so on. So sometimes the part of the realization system is more than just an organization, more than just a company. There's many kinds of elements that are part of your realization system. So to have the most effective intervention system, you may need to re-engineer your realization system also. So system engineering is more than just engineering that intervention, but also maybe working with the business managers, working with project managers to maybe reorganize, to acquire new facilities, maybe to provide new tools and techniques, get new information, gain new knowledge, new services and utilities, change the process. So we need to consider the entire realization system as part of the success of the intervention system in addressing that problem. So the intervention system will become a different system when you deploy it into the context. So an example, Boeing 747 is one design of a particular model of aircraft. But when they deploy that into the context, it comes out in various model variations for different contexts. There may be Dash 100 for the North American market, maybe the Dash 200 for the European market, because each of those contexts might have different regulations, different needs, different operational parameters, and so on. And each one that you build has a different serial number. So even all the down to 100, of all the ones you build, every single one is different somehow. Even though they all conform to the design, the manufacturing process has variations. Even after you deploy it, you maintain the system. Each system is maintained individually, and they will change over time. They don't all behave exactly the same way. So what you're trying to do is maintain it in a safe condition during the entire operational life. So you have to keep track of the variations of these things as they go on. So the point system is more complex in the sense that it's not as you originally designed it. Because there may be variations. There may be modifications in the field because the design engineers, the project is gone, they can't go back and redesign it, so they have to make some field modifications to then continue the life of that system. So when you deploy the system, the context you started with becomes modified. So the realization system needs to understand the original context, but they also have to need to understand, do a projection to the future of how will my intervention in this problem modify the context, because you may actually cause additional problems by changing the context in a way that you did not anticipate. So let's say this is your deployed system. When you deploy it to the context, this thing in the new context will modify the way everything else works. So when we see problems in the field, we need to understand how do we change the context, because that might be, we have to maybe continually solve new problems as they come up. So it's very common for a deployed system to cause other problems. So we need to understand, as we deploy these systems, anticipate these problems whenever we can. And hopefully, this problem is not as bad as the old problem. We will always have new problems. So if we anticipate those, we're trying to get the total set of problems to be less harmful than the original set. The problem is, some of these problems are unanticipated. They're unintended. We didn't intend a lot of the problems to happen. So, better modeling, better understanding of engineering, better understanding of technology, that helps somewhat, but you will never have totally accurate prediction of the future, especially with complex systems. And whenever you have people as part of your system, people are very unpredictable. So if you have to take account of, what if people do things they're not supposed to do? That will have some impact on the success or failure of the system. People can cause a safe system to become unsafe. People can cause a secure system to become insecure. No matter how much you train them, no matter how much you can train them, no matter how much safety features you put, no matter how much security features you put, you still need to have a system that is robust to unanticipated consequences and actions of elements of your systems. We rarely have any systems out there deployed that don't work unless they collaborate. So my mobile telephone by itself is not useful unless it collaborates with the network that connects each other's phones. So the value of this system is often highly a function of the collaboration that happens with other systems. Also, my deployed systems need help and need sustainment. They need to be maintained, they need to be repaired. There are people who are operating them, need help to operate them, and they need to call technical support and say, how do I do this? They may need a resupply of batteries, they may need to be a refresh of technology. So there is a sustainment system to sustain it. So here's the different kinds of sustainment systems you might need to consider that the deployed system depends upon. Now the sustainment system may be pre-existing. In many cases, your repair depot already exists. So when you design your intervention system, you may need to understand the repair depot and how it works. Sometimes you may need to go and say, well, my repair depot needs to be changed to make my support system more successful. Waste removal may be a problem. If you're building your product with materials that may have environmental impact, well, you may have to take account of there may be issues with safety or issues with regulations if you don't account of how do we remove the wasteful products. Many of our systems need continuous supply of food and water. So the various sustainment systems that either pre-exist or have to use, or you may have to modify those to make your support system more successful. So the seventh and final samurai system is a competing system. So you have some competing systems that are trying to address the same problem. So when you have two systems out there working on the same problem, sometimes by them working against each other, it makes the problem worse. Also, you have the competition in terms of if their competing system gets there first, your system may come along and be better, but it's already too late because they already invested into a sooner to market solution. And it may not be as good as yours, but it got there first. So it's competing in terms of attention from the users and from the buyers. It may also compete with the waste system in terms of shared resources. So some of the competing systems in the context are like competitor systems. Users will always try to solve problems themselves, or the status quo, which is do nothing. People have inertia. People don't want to change. So that is one of the competition is going against the resistance of people for changing. Because all of our systems will have some impact on people, and people do not want to change. So we need to understand this resistance from people. So when we're getting into the psychological and social aspects of the success of our system. There are shared resources. My mobile phone has shared resources in terms of bandwidth on the network. If everybody's on the same network at the same time, trying to watch videos on their computer, on their phone, then everything slows down because they're competing for a limited resource. There may be limited fuel and energy available for the various systems. There may be limited attention span, because people only have so much ability to take in information. And we have a problem with our users and our operators that we design our systems that overload the sensors, or it makes them feel not an important part of the system. So we have a lot of systems that are unsafe because the operators are bored and they get tired and they make mistakes. And part of that is because of limited attention span and sometimes psychological expectations. So the human has certain expectations. So if you use a certain color or a certain shape, well, symbols mean something to somebody. Colors mean something. So you need to understand, how will the people react with my system? So these are the 7 samurai. So you can apply the PICARD theory to each one of these systems, because each of the 7 systems has charts. There's interaction within the system, interaction between the 7. There's different contexts. There's original context and there's modified context. All the systems have their own actions. They all interact with each other. They all have relationships. And they all have different destinations. My context system by its own will have its own place it's going to be if you don't do anything. And it will have a different destination if you deploy your system in this manner. So the PICARD theory can be applied across all 7 samurai. So these are the 7 samurai. But between all these are 15 relationships. So if your focus is only on the intervention system, the main thing, our product, our engineering product, you may not take into account the whole solution. So any one of the samurai was very smart, strong, and cunning, but all of them cooperating together was able to solve the problem of the village more effectively. So if we as system engineers don't account for all 7 samurai, then we may be fighting a losing battle with the thieves that are attacking the village. So what can we conclude from this? Our system engineers tend to focus most of their attention on the intervention system. Why? Because that's what they're taught. They're taught as engineers, I have this product, this device, that I'm supposed to engineer to solve that problem, but they don't consider all the systems and how they interact. They might not give you the best holistic solution. So this framework, the 7 samurai framework, can be a tool by which you can enhance the ability to do more proper system thinking. So this 7 samurai is really just some principles and concepts. What you really need to do is build this into your standard methodologies engineers use, the methodology that your systems project teams will use. In many cases, the entire business needs to take account all 7 samurai. So this morning I talked about, first, the PICARD theory, parts, interactions, context, actions, relationships, and destination. So that is a tool, a lens by which you can better see the whole system. So system thinking is hard, but if you have good tools and methods, honoring good system principles and concepts, then you have a better chance of having more holistic solutions to the complex problems we have today. Thank you.